Having looked at conditions under which solubility product holds and equations for solubility of sparing with soluble salts and expressions for solubility product constant, let us see how can we determine solubility product experimentally. So that is experimental determination of solubility product, Ksp. If you want to determine Ksp, you can use any of the following methods depending on which salt whose Ksp you want to determine. The first method is direct titration. Direct titration, whereby you identify the electrolyte whose Ksp you want to determine. For example, if that electrolyte is magnesium hydroxide and you want to determine its solubility product, this one must be titrated with a dilute acid. Its solution is titrated with a dilute acid. The dilute acid can be HCl, it can be nitric, it can be any dilute acid which will not form an insoluble salt with magnesium. So here even dilute sulfuric acid can still work. So that's what we call direct titration. If it is maybe an oxalate like calcium ethane dioate, here you may think of titrating it with acidified potassium permanganate, such that a redox reaction occurs between the permanganate ions in acidic medium with the oxalate ions. And there you can determine the concentration of oxalate ions, work backwards, determine the solubility of calcium oxalate, and hence its solubility product, as we are going to see. That's all about direct titration. The same method of direct titration can be used with salts like iodates. For example, copper 2 iodate. If you want to determine its solubility product by direct titration, then you can analyze the concentration of iodate ions in solution. How is that done? You acidify the mixture and then titrate it with iodide ions such that you liberate iodine. Then the iodine liberated is titrated with sodium thiosulfate. You know that reaction. You liberate iodide ions and tetrathionate ions. So this is like a back titration. You work backwards. Okay. You get the concentration of iodine, relate the concentration of iodine with iodate ions, such that you can get the solubility of copper 2 iodate, hence the solubility product. So basically, these are the kinds of salts whose solubility product constants can be determined by direct titration. The other method we can use to determine solubility product is using conductivity measurements. You can use conductivity measurements. And this is the method that for me, I mostly prefer. Why do I prefer the method of conductivity measurements? It's because this method works for any salt you will think about. Any salt or any electrolyte you think about, this method works. But direct titration, we have seen, is somehow limited to some of these salts. Some of these salts, that's where it is somehow limited. It cannot work for every compound. For example, I may have a sulfate. What do I titrate a barium sulfate with, for example? If I want to determine its solubility product, it may not work for me. What do I titrate with silver chloride if I want to determine its solubility product constant? So in such a case, we run to conductivity measurement as the most probable method. I prefer it than any other method. However, we shall examine all of them in this topic. The other method we can use to determine solubility product is the most uncommon one, whereby we use electrode potentials. We shall see this later. Even conductivity measurements, we shall explore it more when we look at the topic. Called electrochemistry. However, I will briefly talk about it in this topic. So those are the three most common methods that you can use to determine solubility product constant experimentally. So the first two methods, we shall use them in this topic. But we shall see more about conductivity measurements and electrode potentials when you reach the topic called electrochemistry. However, if it's an examination, any method can be used, for you are not always restricted. Are we together? Now let me see an experiment to determine solubility product of maybe magnesium hydroxide. How do you determine solubility product of magnesium hydroxide? I'm going to use both methods. I'll first of all use the method of direct titration, and then I'll use the method of conductivity measurements. Let me use direct titration first. By direct titration. So first of all, analyze. This is magnesium hydroxide. I've told you, if you want to determine its solubility product, it's a base. Titrate it with any dilute acid. But if you're titrating it with any dilute acid, remember this is a solid. You must dissolve it in water until you form a saturated solution. And then you filter off the saturated solution, measure known volume of it, titrate it with a hydrochloric acid of a known concentration. So what shall we do? We shall say excess solid. An excess of solid magnesium hydroxide. It must be excess. Is added to a given volume of distilled water. Known volume of distilled water in any container. It can be a beaker, it can be any container, it can even be a cup. You add an excess of it such that some of it dissolves, some doesn't dissolve. Okay? So the mixture is then shaken. For some time and left to settle. At a given temperature. Remember, we said solubility product is only valid when temperature is maintained constant. So we must specify at a given temperature. Why do we leave the mixture to settle after shaking? So that that mixture can attain what we referred to as dynamic equilibrium in our previous lessons. Are we together? So the mixture is then filtered. We now filter. It's then filtered. Why do we filter? We want to obtain a saturated solution. Remember, we add excess solid magnesium hydroxide, some dissolve, some doesn't dissolve. So we filter to obtain our saturated solution, and we put away the undissolved excess magnesium hydroxide to obtain a saturated solution of magnesium hydroxide. This one is obtained as a filtrate. The residue, we don't need it, so you may not talk about it. That is the excess undissolved magnesium hydroxide. Now you get a known volume of the saturated solution, which is now a filtrate. A known volume of the filtrate is pipetted. Why do we use a known volume? We are going to use that volume in calculations. Is pipetted into a conical flask. We are now going to titrate it with a standard solution of an acid and titrated with a standard solution. Which acid can we use? Which acid can we use? Choose an acid of your choice.
Sulfuric acid.
Standard solution of dilute sulfuric acid. But you must be very careful. If we are determining solubility product of maybe calcium hydroxide, then we cannot use sulfuric acid. Why? We are going to again form an sparingly soluble calcium sulfate, and the reaction may not proceed. So sulfuric acid may not work for calcium hydroxide. Even, it may not work. Hydrochloric acid will work under nitric. But here sulfuric acid is working since this is magnesium sulfate being formed. The standard solution of dilute sulfuric acid. Specify the indicator you are using. So we shall use methyl orange indicator here. Then you write the equation for your reaction. Calcium hydroxide, aqueous, plus, remember it is a saturated solution we obtained. Give us, this is sulfuric acid. Oh, I'm thinking of calcium now. This is magnesium hydroxide, sorry. So we have magnesium hydroxide plus sulfuric acid, giving us magnesium sulfate and water, a self-balancing equation. So this is the sulfuric acid that's going to help us work out the treatment of results. So after knowing this, what shall we do next? We shall now determine the molar concentration of magnesium hydroxide is determined using the equation above. Using the equation above. So taking the molar concentration of magnesium hydroxide as X moles per liter. What shall we have? Let's now see how we treat the results. We have magnesium hydroxide. Right now the equation for its solubility, giving us magnesium ions and 2 hydroxide ions. So this one we have got it by calculation. We don't go into those details. However, everybody knows that you have the volume of sulfuric acid that reacted. Okay. If you have the volume of sulfuric acid that reacted, calculate the number of moles of sulfuric acid. Because its concentration is known, it's a standard solution as we have seen in our experiment. Using molar ratio, get moles of magnesium hydroxide reacted. Those moles are the one in the known volume used V. then you get the concentration of magnesium hydroxide. I hope I'm understandable there. So that gives us the molar concentration of magnesium hydroxide, and we assume by after the calculation it is the x moles per liter. So since molar ratio of magnesium hydroxide to magnesium ions is 1:1, this implies that the concentration of magnesium hydroxide, molar concentration, is equal to the molar concentration of the magnesium ions and is equal to x moles per liter. Are we together? And since I'm getting all this information from this equation, and since the concentration of magnesium hydroxide not the concentration, but the molar ratio of magnesium hydroxide to that of hydroxyl ions is 1:2. What does this imply? This implies that the concentration of hydroxide ions is equal to twice the concentration, molar concentration of magnesium hydroxide, and that is equal to 2x moles per liter. The moment you know that treatment of results, things become very simple for you. So from this, what is our Ksp expression? Ksp is equal to magnesium ion concentration molar multiplied by the hydroxide ion concentration molar squared because of this 2 here. This will give me the concentration of magnesium ion is x multiplied by that of the hydroxide ion, which is 2x. This gives me this is 2x, but the 2x, the whole of this is 2x. We have seen it here. But this hydroxide ion concentration is squared. So when you work out the mathematics here, you get 4x cubed. The units will be also cubed. It will be mole cubed per liter, or mole cubed, this one per -6. Is everything clear, Muhammad?
Yes, sir.
This method here is used to determine the solubility product constant of any sparingly soluble hydroxide. How shall we earn our marks here? An excess of magnesium hydroxide, a given volume of distilled water, mixture shaken for some time, left to settle, given temperature to attain equilibrium, filtered, get a saturated solution of magnesium hydroxide as filtrate. A non-volume of the filtrate is pipetted into a conical flask, titrated with a standard solution of dilute sulfuric acid. Mention the indicator, write this equation. Get the molar concentration of magnesium hydroxide, give it a notation, that's the equation. Give this a mark, give this a mark, we give this treatment a mark, the expression for solubility product, and your final answer. So that would be our experiment. Unless there is a question, I would wish to proceed. That is one method which I have said may not work for every salt or every sparingly soluble electrolyte. I want to use the second method, which is that second method is now conductivity measurements, using conductivity measurements.